Thank you so much for inviting me to Newton Institute. About 20 years ago, we started on working on something that today is called exact recurrent structures, or what I prefer, which is term recurrent flows. We were successful. It became clear that we're not making any progress by making these domains larger. And in our last collective meeting in Santa Barbara, I realized that we have to change the way we think about problem of turbulence in a rather radical way. And I'll try to explain it again today. The main idea is to give up evolution in time and think of problem of turbulence as a problem of enumerating admissible spatio-temporal patterns. When you look at turbulent or chaotic systems, the main idea of chaos, as opposed to kind of things you learn in physics courses. In physics courses, you basically, only thing you ever learn is harmonic oscillator, is Hooke's law. When you push on something, it resists and acts against it. And if it does it proportional to displacement that you cause by your push, that law is called Hooke's law, and result is oscillating solutions. Chaos and turbulence are very different. Instead of having a bottom of potential in which when you perturb a little bit, you run around the bottom, you have an inverted potential. So locally what happens is when you push, if you imagine that you push, the cat doesn't resist, it just runs away. Mathematically, the solutions are only the same. Instead of being sines and cosines, there's sinus and cosinus. I'll try to explain how this works. In three-dimensional world inhabited by plumbers, we visualize fluids as some three-dimensional volume, space this way, space that way, and there is a space another way, third dimension. But then there is also time. We observe a fluid. At every instant in time, we take a snapshot. Now, I cannot draw the snapshot because every point in the three-dimensional space has velocity associated with it, which is 3 dimensions. We take succession of such snapshots and we construct a video. Only computers can comprehend this video. Now, this is a conceptual talk, so I'm trying to explain how this is going to work if you are going to solve problem of turbulence. So for purposes of this kind of talk, I will think a little bit more like electricians, for example, cardiologists that looks at the surface of the heart and sees a two-dimensional colored scheme, which is electrical activity or scan. We'll take a one-dimensional fluid. That one-dimensional fluid, and there'll be space this way. So we'll take succession of one-dimensional shots, and then each instant there'll be a velocity which is one-dimensional because space is one-dimensional. So in the way that a flame front changes its height is one-dimensional. So something that's orthogonal to the space. And we can consider this a scalar field, just a one number. We have captured space and time on three-dimensional plane, and the third dimension, the velocity field. Now, when you do experiments, what you see is that there are many correlations in that because we see shapes changing in time. But when you look at one of these systems in space-time, you see patterns. Do we have mathematical language that says what patterns are allowed and what is the catalog of admissible patterns? Our task is to describe clouds. And at this point, Eberhard Hoff, 1948, comes in and says, the ultimate goal, however, must be a rational theory of statistical hydrodynamics, where properties of turbulent flow can be mathematically deduced from the fundamental equation of hydrodynamics. And this is what we we'll be doing. There are no statistical assumptions in anything we do. Everything follows from the equations of motion. Navier-Stokes, Euler, Kuramoto-Shivashinsky, you choose it. In the spirit of the moment, the sheep are Welsh. Why do we have sheep in a field? The visualization that comes from 19th century German mathematics essentially is to say that we have a field, so we have a piece of ground. I'll call it parquet floor because I'll tile it in a regular way. And on every piece of that field, there's a blade of grass. And one of these blades of grass, and that's the scalar field we're discussing. At position C, will have this value. To make further progress toward this field theory, we have to discretize things because computers cannot represent infinitely many values. So in these two-dimensional examples, we'll start as our continuum spacetime, but we'll represent it every point by a pair of integers. This is still too big. So we'll take these integers to be modulo a finite domain, L in direction 1, L2 in direction 2, and the integer will just run from 0 to L2 minus 1. And because we want translational invariance, we'll make these domains periodic. So basically, we're replacing two-dimensional spacetime with integer valued tori. In this field, we used to have x divided every point, but now it gets replaced by a finite number of numbers, where each one of them is a function over reals. This is called scalar field theory. This latticized, so this is lattice scalar field theory. We are taking our space time. We think of it as a parquet floor. It's covered by regular tiles or parquets. We can account for each one of them just by specifying one point. We usually make it a unit lattice with unit spacing. And on each of these lattice side, there's a little blade of grass, and that is the state of the cat. You'll see why we call this a cat. This is actually a technical term. And thus we have turned our problem of enumerating, characterizing spatiotemporal patterns or shapes into a lattice field theory. This is a finite problem, but a high-dimensional problem. However, Hopf has something to say. What Hopf has to say is another level of madness. Hopf says the geometrical picture which we are just constructing, the state space of possible states of fluid, is cool. However, it's not the most important problem of turbulence. Of greater importance is the determination of the probability distribution associated with the phase flow. So how does that work? I'll start by assuming we know nothing. Eberhard wants us to describe a probability. If you only had a lattice with one side, we would say, well, probability should look like something that's the most likely thing and unlikely things. So it should look something like that. It should have some width. Let's call it 1 over mu. It should have a mean, it must be a Gaussian. It's something that looks like mu square phi c minus the mean squared. Now suppose I take two sides. One side is in Atlanta, but the second side is on the moon. Then I can say the probability of my two-side system is a product of the two probabilities. Now, when we multiply two exponentials, the exponents add up. Now, if we assume that the same laws of physics apply here and in Saint-Jean, then that should be translation invariant. That is to say, we expect the mean to be the same in both locations. What we decide is the origin of how we measure the strength of the field is arbitrary. So we can set the mean to be 0. And now we can write the probability of any number of sites as long as they're not correlated. First, let's define a lattice configuration, capital Phi. Suppose we have some finite slab which is covered with lattice sites. And on each of these lattice sites, there is a little column which is the value of the file at this lattice site. And that's what we mean by a given field configuration, means a bunch of real number, one real number for each site. If they don't know about each other, the probability, it's exponential. The thing in exponential we call action. So the action, an amazing function, it takes trillion numbers and returns one back, returns the sum of squares of the field every place, because probability is multiplicative. So this sum is additive. There are infinitely many probabilities. So how are we going to compactly discuss them all? That problem has been solved in statistical mechanics. It's called partition function. And it says, I can take each probability which we have written in this exponential form. So for each configuration, we have the value of the action. Add a linear term dot another set of numbers. For each lattice site, there will be such a number, j, called a source, little j at site z. We can take all these probabilities. We can integrate over all possible values for each site. So we write the humongous integral, one dimension of it for every lattice site. The result will only depend on the values of the source field. That's what's called partition function. What's good about it? Big J is a vector of J1, J2, Jn, which is the total number of lattice sites. When we take derivative of this thing, and then we set this J to 0, what will happen is this thing here is, remember, probability of all these guys being in the lattice configuration J. But this derivative took only one component down. When we set this to 0, this is now expectation value. If you take a second derivative, I have same probability distribution, and I look at the correlations of these guys. That's why people, in any situation where there are lots of little bits you have to keep track of, but there are some basic laws like translation invariance, homogeneity, isotropy, collect them all into partition function. It's a generating function for all probabilities and all expectation values of anything. So it's basically a total content of a theory that's described by probabilities. There is one problem with this theory. It's ultra local. When we constructed this, we started this know nothing. All of these guys know nothing about anybody. All these integrals are trivial Gaussian integral, and this has no content. It's a total bore. Now, the reason why I brought you to your attention anyhow is that next we'll introduce correlations. Ultra-local theory is boring. What do? We need some correlations. The simplest way to have a correlation is talking to my neighbors. How do we describe that? If we own a lattice, let's include the term I'm at Z and I'm talking only to the people if the distance on a lattice between these two sites is 1. So that's as local it can be. Wherever we are, That means that it's actually a function of the difference between the two, because that's a translational invariant combination. It's same every place. Then we would like it to be isotropic, meaning that I can set C to be 1 if I have any nearest neighbor, 0 if I'm not the next neighbor. Putting all this together, you get Laplace operator. And I compare what I'm doing with all my neighbors. So sum over Z prime such that the distance is 1. For example, in one dimension, there's a minus here, plus here, minus here. If I'm on a two-dimensional lattice, I'll look at myself 4 times. So it's a very simple modification of our action. And now we have free field theory, a bunch of harmonic oscillators. This is bilinear in fields. When we put it in exponential, this is Gaussian in fields, so we know how to solve it. We go to Fourier modes, We've assumed translation invariance, what is called Klein-Gordon mass, is same everywhere. I can combine these terms and write them as a matrix on a diagonal. Now, and off diagonal, just in one dimension, just talks to its neighbors. 0 every place because we don't talk to anybody except closest neighbors. And when we get to the ends, we have to stick -1 here and -1 here. These are the boundary conditions, they're periodic. But this parameter, which I call mu square, if it's negative and I look at solution, I'll get oscillations. We'll have solutions which are oscillatory, like a matrix. But if it's positive, what particle physicists call Klein-Gordon mass, then we only have exponentials, cinches and quotients. What you learn in school usually is this case, and what you have to learn in chaos and turbulence is this case, where everybody is unstable rather than stable. This is all very cool, but if you push something too hard, it actually doesn't always respond proportionally to your push. It might get stiffer, it might get softer. In other words, oscillators can be anharmonic. It's the most typical case. You sum up over everybody, add to it a quartic term with some strength. This is what kind of general scalar field theory looks like. Why am I subjecting you to this? I have to remind you about something that's very special to deterministic dynamics. All you need to know about determinism. This probability that we started with, in determinism, it has to be very narrow, because what we have in determinism, if you have an orbit that's connected by equations of motion, which I'll derive in a second, then there's only one solution for any particular state that's part of such orbit. So this probability will be so narrow, it'll have to be a delta function. It is intrinsic to determinism. It makes it different from quantum mechanics, and it makes it different from stochastic processes, for which the probabilities of necessity of some width. What does this mean for us? If we take this action and we vary it by any field on any lattice site, the variational principles of mechanics say I have to find solutions such that this first variation is 0. If you were doing this in quantum mechanics or statistical mechanics, you would say the most important parts are the stationary parts. In other subjects, this is an approximation. But for Lagrange and for Euler and for divinity that thought of all of this, this is the mechanics. You're only allowed to use these solutions when you deal with determinism. We'll call these solutions lattice states. So remember, we are computing probabilities of states. The probability of this state is such that I must satisfy Euler-Lagrange equations, and that is very sharp condition. It's a Dirac delta. And now this gives us a deterministic partition function. I actually know how to integrate over delta functions. Only contribution is where field is exactly where it is. And this is a function of the field. So you have to transform coordinates by Jacobian. And I get determinant of the Jacobian of this transformation. And that's it. A determinant's of volume. So the state space is n-dimensional for scalar theory, but there are n possible lattices. And this is the volume, n-dimensional volume that describes the neighborhood of my deterministic solution. What's this thing? The first time I found it is in a paper by Hill from 1884. So I call it Hill's determinant. The Jacobian was a derivative of that function. That's what we call orbit Jacobian. And its interpretation, it's a Jacobian of what happens if I perturb every site on that lattice. Determinant of that thing, that's what we call Hill's determinant. Why do we care? Because that's the weight associated with particular classical solution phi c, which is now spatiotemporal solution. When you compute it, I'll just show you what it looks like. It's a banded matrix. On diagonal, I pick up the potential, evaluate on the diagonal, and then Laplacian, it just says, well, I have to see what's going on left and right. So there are two bands here. There's a periodic boundary condition. These determinants can be computed. Hill and Poincaré computed them. They have to do with translational invariance. So that means that discrete Fourier transforms will diagonalize them. We can compute thousands of solutions. And by those, I mean also Navier-Stokes and Kuramoto-Shivashinsky are field theories in this sense. And I'm sure you people in this audience can compute it for Navier-Stokes if you wanted to. Now, you might say there is a way every orbit owns a fraction of the volume. So I'm partitioning space in neighborhoods. So if I randomly throw something in the state space, it'll land in one of these neighborhoods with the probability, which is given this guy here, this weight. It's deterministic system, but it probabilistic interpretation comes through it in this way, that the state space is deterministically partitioned. Now, once you have this, you have things that we call cycle averaging formulas. I'll give you a very mangled sketch. Once you have this information, you would like to predict the friction on the walls of a pipe or dissipation. So I would like to have some observable, how much energy I burn in this particular part of the state space. You'll find some formula. It says the A is computed over the lattice. So I measure every lattice site. You can compute correlations. And now in the kindergarten version of the theory, you have probabilities that you will be in the neighborhood of a particular classical solution of your equations of motion. Measure my observable on each contributing solution, some configuration in space-time, and I will get the average of that quantity. I will be able to compute them once having computed the exact covariance solutions, a sufficiently large set of them. I'll be able to predict all observables average over space-time, like some climate thing, like increasing mean temperature of the surface of the ocean. Now, you don't believe me because you're working people and I'm just telling you something. So please give me a break. Go read Chaos book. If you don't have time to read, take the online course. You will discover, to paraphrase Bob Dylan, oh, you've gone to the finest schools, but nobody taught you this, and you need it. I'm done.